All through this course, we've seen examples of the way modern telescopes have opened our eyes to new phenomena. The outstanding advances have been in detectors, and we'll look at some of those in a moment. But astronomers don't just put a suitable detector at the focus of a telescope. There are vital and often quite complicated optical elements for the incoming radiation to pass through before reaching the detectors. No two instruments are the same, but there are some common elements. The first component might be bandpass filters to choose the particular wavelength region for which the detectors have been designed. Then there will be a lens to give the beam the degree of convergence, what's called the F ratio, suited to the input aperture of a spectral analyzer. Then inside the analyzer itself, which may be a simple diffraction grating, but more often is a combination of a coarse grating, called an A-shell, and a fine grating. This combination spreads the spectrum out into a series of bands to give high spectral resolution and broad coverage. There will also be several mirrors to switch the beam between different lines of optics, leading to different detectors. One of these will be to a camera to provide an image. Some sort of image will always be needed to locate the source. Not usually as obvious as the sun, of course, often just a faint star or a distant galaxy. Sometimes the astronomer's work will be based on an image, which must then be of the highest quality possible. But for every image, there will be many spectra to be recorded to work out the chemistry and dynamics of the source. This optical instrument maximizes efficiency because the spectra for an array of points in the image are recorded at the same time as the image itself. The same thing is done in radio wavelengths. Here are some results displayed as images at different wavelengths, but they could also be displayed as spectra at different points. So big, expensive telescopes use very sophisticated, powerful detectors. In the case of telescopes for spacecraft, they must be assembled in huge clean rooms like this one, where one entire wall is made of air filters.
This is the largest clean room at Goddard Space Flight Center. We use it for processing payloads for the space shuttle, especially scientific instruments to go onto orbiting satellites, sometimes whole satellites. We take the equipment, we test it in here, we assemble into larger modules and basically get it ready for a launch into space. And in those scientific instruments, the most important components are the detectors that receive the radiation. An incoming photon of light strikes the detector surface, releases electrons that travel on inside the detector, and we detect them and count them and measure the radiation by that means. All across the electromagnetic spectrum nowadays, these detectors are approaching their theoretical sensitivity limits. So they're getting about as good as they can get in most cases. And they're different in every energy range. The infrared, for example, we use the two-dimensional arrays so we can make an infrared picture that are made of such materials as indium antimonide or mercury cadmium telluride. And by selecting different materials for your detectors, you can detect different ranges of the infrared wavelengths. In the optical or visible light, we're using primarily the charge-coupled devices. These are, again, two-dimensional arrays. They're extremely sensitive, and you use one of these arrays nowadays with, say, a 1-meter diameter telescope, and you can take a picture that's as sensitive, you can see as far out as you could 10 years ago with a 4-meter telescope, just using photographic film, the way we used to take these pictures. In ultraviolet light, we've used such detectors as the digicons on the Hubble Space Telescope. And in these, an image of the spectrum, the incoming light, is focused on a photocathode, and it produces an image of the spectrum in electrons that are magnetically focused within the tube. And they fall on an array of diodes. And each diode counts electrons corresponding to a different wavelength in the spectrum. We call it an electron image of the spectrum. You detect the ultraviolet light in that manner. There are two-dimensional detectors now for ultraviolet light, in which you can make an observation, for example, in which you have one dimension in the detector that's a spatial dimension on the sky, and one dimension on the detector that's the spectrum. The wavelength varies along that dimension. And you can make an observation in which the spatial dimension is the radius coming out from the center of a galaxy. And so in one exposure, you can simultaneously record the ultraviolet spectrum at each point along that radius. And we call this a multiplex advantage. In one observation, we can get many spectra that previously we would have had to move the telescope to take a spectrum at each separate location.
We want to do this in space because we want to look in the ultraviolet in order to look at all of the absorbing lines which naturally occur in the ultraviolet. These can be shifted at very large distances into the visible, so some of this work is done from the ground. But we have a gap in our knowledge. If we look only from the ground, we can only see what happens very far back in time, and we can't connect it to what's happening now. In order to connect it to what's happening, say, in the last 5 billion years or so, then we need to look in the ultraviolet, and that's what we'll be doing. For this, we need detectors which are specific to the ultraviolet, which are not sensitive to the visible and are only sensitive in the ultraviolet. Such a detector you can see here. This is a microchannel plate, and we coat this with a cathode which is only ultraviolet sensitive. This particular detector has 1,000 elements in one direction and 1,000 elements in the other direction, so you get 1,000,000 picture elements overall. If you look in a microscope, then you will see that this is composed of millions of tiny tubes. Each of these tubes takes in an ultraviolet photon and converts it into an electrons and amplifies it so that you get about 1,000,000 electrons out of the back. Then in a particular device which was invented by Dr. Gethin Timothy of Stanford University called the multi-anode microchannel array, in which each electron cloud is picked up by the electrodes and converted electronically into a signal which identifies the position on the array. This is called a photon counting detector. So we will use ultraviolet observations from space with visible observations from the ground in order to put together the whole history of the chemical evolution of the universe in time.
In the X-rays, you have the advantage for making images now of the nested grazing incidence mirrors. The X-rays glance off one of these mirrors. You can focus them and make an image in X-rays that goes into a gas-filled imaging proportional counter like are used on the ROSAT X-ray satellite, and then the X-ray photons in that image cause electron events in the chamber which you can count, and you know at what position each event occurred, and you build up a picture of the sky in X-rays. The gamma rays, there are different kinds of detectors for each broad range of gamma ray energies. On the Gamma Ray Observatory, we've used spark chambers for the energy range from the tens to the hundreds of millions of electron volts. That's the energy of each individual gamma ray photon. What happens is photon comes in, it passes through a thin metal foil, produces an electron-positron pair that move on to the spark chamber, which is gas-filled cavity between two of such foils, and it causes an electrical discharge that we can count, and that's how we detect the gamma rays. Some of the gamma rays pass right through, and they go to another foil or another before they actually create a pair. And so you have a series of foils and spark chambers in such an instrument, and that's how we record even the gamma rays, which was almost unthinkable not many years ago.